Welcome everyone to this analog discussion 4. So I will be presenting something, okay? Or should I make a whiteboard? Hello.
Yes, you should present.
Okay, I should present. Okay. It is visible, right?
Yes, yes,
Okay.
yes, visible.
So this will be discussion 4. Okay. So let's some example of RLC circuit with current excitations. Okay. So first circuit will be this. Okay. So initially, okay, so all the cases, okay, we will be discussing capacitor with some initial conditions and without initial conditions. Okay, so for this circuit, let's say first case, the VC of 0 was, let's say 2 volt. Okay, this is the initial condition. And second
Okay.
case, okay, make first, this is 0 volt first case. So this is initially uncharged. Okay, uncharged. And second case, the capacitor is charged to, so let's say this, charged to, let's say at 2 volt. Okay, so this is initially charged, charged to 2 volt. Okay, and the polarity will be look like this. Okay, the initial conditions. Now we have to draw, like we have to plot V out versus time. Okay, versus time, and this is a unit step. Okay, okay, so let first make it unit step, then it will be of a pulse. Okay, okay, two cases. One case is step,
Okay, okay.
another case is pulse, and another like other case will be impulse. Okay, three cases. Okay, make it four cases, and another will be ramp. Okay, so now, so first case is step. So we know that the voltage across a capacitor is nothing but the integration 1 over C integration of IC times dt. We all know that, right? So, and if this IC is constant of like step, so this will be outside of this integration, right? So this will be nothing but IC by C into T, right? So
Yes.
if we plot first case when the input step current, so we know the output of the voltage like the voltage output will be nothing but a ramp, right? We all know that. So this will be like this, right?
Yes.
Now the question is how much the capacitor can charge, like it will it go to infinity or not? So it cannot, like infinity is not possible, right? So infinity is not possible. So the capacitor will charge up to its dielectric breakdown, right?
Yes.
So let's say, like assume for a numerical value the dielectric breakdown voltage of the capacitor is, let's say, 100 volt. Okay, so it will reach 100 volt, then it will stop charging. So this will be like this. Okay, so this is, let's say, 100 volts, right? And
Yes, yes.
this is for this case when the capacitor is initially uncharged or charged to 0 voltage. Now the second case will be when the capacitor is initially charged to 2 volt. Okay, then what will be the output, like what will be the changes? So this will be nothing but a small change where the output will try to make like charging from 2 volts, right? So this is 2 volt, this is 0 volt, and then eventually it will like limited to 100 volt as said previously. Okay, so this will be the only changes when
Yes.
the capacitor is initially uncharged and when the capacitor is initially charged to 2 volt. Okay, clear?
Yes. Yes.
It
Okay.
is start from 0 volt to 100 volt, and it is charged like start from 2 volt to 100 volt. Okay, now what is the time constant of this circuit? So we know to find the time constant, we do all the independent sources are inactive, right?
Yes.
So the voltage source will be short circuited and the current source will be open circuited, right? So let's do it, and then we find the equivalent resistance of the circuit and equivalent capacitance of the circuit, and the time constant then will be R equivalent times C equivalent. Like for a RC circuit, okay, if there is RL circuit, then we have to do these things and find the equivalent inductance, right? Then we have to make time constant will be nothing but then L equivalent divided by R equivalent, right?
Yes. L by R.
Okay. So for this circuit, we know that if this is open circuit, so there is circuit like this, right? Now here we can see that the equivalent capacitance is nothing but C itself, right? But what will be the R equivalent across this C? So R equivalent is nothing but infinity here, right? Because
Yes. R
because
equivalent
in
is
this
infinite.
open circuit having an impedance of infinite, right? So in this circuit, time constant becomes infinity. Okay. So from this graph, we can also comment intuitively that the capacitor is charging to infinity, right? So the time constant must be infinity. Okay.
Yes.
Okay. Now come to the second case when our input is a pulse. Okay. So let's say this is t. Let's say t equals 0, and so this is the time graph. Okay, let's make it. And let's say this is on milliamps. Okay, and we have to plot V out. Okay, okay. So okay, let me change the color of the pen. So and in this case, we are assuming the voltage across the capacitor initially was 0 volt. Okay, for simplification. Okay,
Okay.
okay. So we know that
And for
when
the
the
pulse, please write it T1, T2,
okay, so
T3.
the time period
Then
will be capital T and this will be 2T. Okay, the time period is T. Okay, capital T.
yes, yes,
Hmm. So now, so we know that when the input is zero ampere, so the capacitor is like the circuit will be looking like this, right? In this time duration,
yes,
so the capacitor cannot be charged, cannot be discharged, right? Because there is no current to charge the capacitor, or there is no ground part to discharge the capacitor. Okay, and the capacitor was initially charged to 0 volt, so it will maintain it 0 volt across it. Okay, so the voltage at this time period will be this. Okay, right? Now for okay, so this will be T by 2. So now at T by 2 to T, the circuit becomes this, right? Like the previous case. So this is 1 milliamps. So we know that the current is fixed, the current is a step or a constant. So the voltage across the capacitor will be a ramp, right? So this is we have already derived, right? We have drawn, right?
Yes.
Now what will be the voltage?
From T by 2 to T time.
Yes.
Yes.
Now
It
we
is a
can,
ramp.
let's say this is V1. So we can find the V1 value putting the time like this T. Okay. Like this will be nothing but 1 milliamps divided by C integration T by 2 to T dt, right? So this will give this amplitude V1. Okay. So we are not concerned about this amplitude. Okay. We are considered like concerned about the waveform, like the shape of the waveform only. Okay. Now,
Yes, yes.
okay, now t to t by, like this will be 3t by 2, right?
Yes.
What will be the picture again?
From T,
Yes, yes, yes,
the capacitor will be hold its value.
yes, again the circuit will be looking like this, right? But as there is a no current, so this will be acts as open circuit, the current source. So the capacitor cannot be charged again or cannot be discharged, so it will hold its previous voltage. So the previous voltage was this, right? So it will hold its previous voltage.
Yes. V1 value.
Okay, beyond valve. And then again at this time duration it will charge ramping up. Then it will hold and it will again ramping up. So
Yes.
it will go to 100 volt as said previously as dielectric breakdown like this. Okay, so it will take many cycles to reach this 100 volts. Okay, so this is a staircase function we can see. Okay, so this was the second case.
Okay.
Now third case was impulse. Okay, so impulse. So let me draw the picture again.
So second case is that when the capacitor is uncharged,
Yes,
and then if the capacitor is charged, then it will start from that value.
yes, it will charge at this value and then this will be this. Okay,
Yes.
okay. Hmm. Okay,
Okay. Okay. Now come to the third case.
yes, third case, this will be third case. So and this is grounded. Okay, so now this is a impulse, right? We know the impulse look like this, and let's say the width of this impulse is x. So x is nothing but the area, right? We all know that the impulse function is a special type of function, right? Now
Yes.
let's say two cases when the capacitor is initially charged to 0 volt and the capacitor is charged to, let's say, 2 volt. Okay, so we will try to plot the two voltages. Okay, so we know that capacitor, what capacitor do, capacitor integrates its current, right? The current flowing through the capacitor, right? Now we
Yes.
all know the integration of a impulse current is nothing but a step, right? Step voltage, right?
Yes. Yes. Yes.
So and the infinite current flows through the capacitor. So the capacitor will change the voltage across it instantly, right? So first case was Vc of 0 minus was, let's say, 0 volt, and second case is Vc of 0 minus was 2 volt. Okay, and what will be the voltage, like how we represent this x? So this is area, right? So
Yes.
area means q, and q is nothing but I into t, right?
Yes. Yes.
So okay, let me do that. So it will start from 0 to a certain voltage, and it will be looking like this, like step output, right?
Yes.
Now mathematically if we look into this problem, so we know that like I want to calculate this voltage. Okay, like this with, let's say, v1. Okay, so v1 is nothing but, we know that like q equal to cv, right? So the this voltage v1 will be nothing but q by c. right? Okay, so here Q is nothing but our X. Okay, so the voltage, like the step voltage, like the amplitude will be nothing but X by C. Okay, got it? The impulse function we denote as a area, right? This is a special type of function. So the area or the height will be X. So X by C will be the yes, step voltage. Okay, amplitude of this step voltage. Okay,
Yes.
okay. So now second case. So you know that the voltage, initial voltage was 2 volt. So this will be 2 volt. Let's say. So it will jumps to 2 volt, from 2 volt to this voltage X by C. Okay. So this is the change only. It will charge from 0 volt. So if I draw this, so this will be t less than 0, right? So here this is t less than 0, and here t tends to infinity in this region. So the picture will be looking like this, and in this case the picture will be looking like this. Okay,
Yes. Yes.
so this was 2 volt and this was 0 volt. Okay, get it?
Okay. Okay. Understood.
Okay, so now and another case. So I haven't seen people analyzing with RAM current input. So let's do it. Okay, in this session. So this is RAM, right? Now what is the indication of RAM? This will be a parabolic, right? Like
Yes.
there will be a some t squared term, right?
Some
T.
T square term. Yes. Yes.
Yes,
Yes.
yes, yes. So we know that we can directly comment on that. So this will be, so current is ramping, right? So I think the waveform will be looking like this. Okay, so we are not going to like analyze this circuit deeply. Okay, so like nobody, I think many people don't analyze this circuit. So I
Yes.
want to just like analysis a small bit of this. Okay,
Okay. Okay.
okay. So I think this will
To
be
get an intuitive idea, it is this. And then I think we have to simulate this and watch what will happen.
okay. We can simulate it and we can do the mathematical analysis as well. So I think this will be this. Okay.
Okay.
Mhm. So okay. Now if I if I make the circuit with modification, so what will be the case here? Same condition. What do you think? What will be the, like we have analysis the I of this is in 4 cases, right? 4 cases. Now my question is, what will be the changes at this V out node? Like like with respect to the previous case, like there was not R, right?
Yes.
So can anyone comment what will be the changes at this V out node?
So when we analyze the time constant here,
Hmm.
the current source get open circuited.
Yes.
So the capacitance equivalent would be C itself, like the previous,
Hmm.
and the resistance is also infinite in this case.
Yes.
Like so, the time constant is not changing from the previous.
Yes. Basically, all the details we have
Yes.
analyzed, this will be remain
Yes,
same as it
it
is.
remains exactly same because there is no path discharging the capacitance.
Yes, 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 exactly. So the analysis will be same, but only one thing. So there was only one node, like one effective node, right? But here there is two effective node. One is X and another is Y, right?
Yes,
So only
yes, yes.
this Y node will make changes, like will be changing this node. Okay, so this is the case. Like for
Okay, okay,
output case, there will not be any changes. This will be remain same at previously. Okay, as we discussed previously. Okay.
okay, okay.
Okay, so okay, let me do another thing with a current source. Okay.
One thing is in my mind. that
Okay.
for the impulse case,
Okay. Impulse case. Okay, I am going there.
the RC is going to behave like the same or not?
Same. It will be same.
Maybe
It will
I
be
don't
same.
know.
Because
Okay,
the
okay.
capacitor property depending upon the current flowing through it. Okay, so this will be remain same.
Yes, yes.
Okay.
And it is in series, so current flows only in one direction.
Yes. Okay.
Okay, okay.
Okay. So now let's make it. So now we are going to give a, okay. So there is this case I and R and C, and we have to plot this V out. Okay, plus minus. So let's, okay, and we are talking about the time constant of this circuit is very less than this time period. Okay, for our easy analysis. Okay, so tau is very less than
Okay.
t. So here the charging and discharging is very fast. So this is the meaning here. Okay. Okay. So let's do the analysis.
Yes.
Okay. Like we are going to do intuitively. Okay, only. So now for this time duration, okay, and the capacitor, let's say initially, okay, let's say capacitor is initially charged to 2 voltage. Okay. 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 So
Okay.
in this time duration t by 2, and this is t 3t by 2, and this is 2t. So in this time duration the current source is open, right? So the picture will be looking like this, right?
Yes.
Now what do you think the voltage across the capacitor, how it will behave? Please, anyone?
If I say the voltage across capacitor is VC, then it gets a path to discharge.
Yes, so the all the 2 voltage will get discharged so fastly, because the time constant is very less. Okay.
Yes. So
So
exponential decaying from the 2 volt, I think,
yes,
happens
it
in
will
this
be
case.
exponential decaying. Why exponential? Because there is a resistive bar. So the current, discharging
Yes.
current will be not infinite. Okay. So the
Yes.
exponentially discharging will be happening. Okay. So
Yes.
okay. So let's say, okay. So this is the axis of V out. So 1 minute. So initially the voltage across the capacitor was 2 volt. Okay. This is 2 volt.
Yes.
Now it going to decaying exponentially, like the capacitor will discharge, right? So it will go like this,
Yes.
and the discharging will be very fast.
Yes. Yes.
Okay.
Yes.
So
So
at this,
mathematically also, there is a e to the power minus t by
yes,
tau
so
format
this will be
is
nothing
there.
but v into e power minus t by tau. Okay.
Yes. Yes.
For discharging case, we all know. And here
Okay.
vx is nothing but 2 volt. Okay. So here we have reached. Now from from t by 2 to t, there is a finite current. Okay, and the current is, let's say, 1 milliamps. Okay, let's say this is 1 milliamps and this is 0. Okay. Now there is a 1 milliamps current. Okay, let me draw here again. So 1 milliamps is current, 1 milliamp current is flowing through. Now what do you think, what will be the voltage output, like what will be the behavior of this circuit? So the capacitor will charge again, right, due to this source.
Yes.
Now question is, what will be the nature of the charging? It is exponential or linear or in like sudden, like instant. So this will be, we all know, this will be exponential charging. Why? Why? Because there is a resistance present, so current cannot be infinite, so there cannot be sudden change across the VC, right?
Yes.
Okay, and the current is also not constant because the capacitive impedance is increasing with time, right? The capacitive impedance is increasing with time because the frequency is decreasing with time, right?
Yes. Yes.
We all know as step function having a frequency of infinity here and frequency of 0 here. We all know that, right? At t equals
Yes.
to 0, the frequency is infinite, and t equals infinity, the frequency is 0. So the current through this capacitor is also not constant because this impedance is changing. So if this impedance is changing and these two impedances are fixed, so current through this impedance is also not fixed, right?
Yes.
Okay, I am telling that
Current is reducing.
yes,
Yes.
like my motto is to say the current is not constant. Obviously, it will be decreasing because the impedance is here is increasing, na.
Yes. Yes.
So
Yes.
so the current through the capacitor is not
Yes. Yes.
constant because the impedance is varying and these two impedances are fixed, so that the current through this will be varying. Okay, not constant. So the charging cannot be linear as well. Okay, so the charging here will be exponential only. Okay,
Yes.
actually we know that the charging will be exponential, but why not linear and why not sudden jump? That I am telling. Okay, that I was telling. Okay, this is the intuition. This is the, like, we
Yes.
can
Yes.
find it anyway, right? So now it will charge to exponentially. Now question is how much it will, like, okay, so let's say, so this will charge exponentially. Okay, okay, let's say this. Okay, now the question, what will be this value? Okay, so now we can see that. So okay, so this will charge to, but like the charging will be very fast, right? So what will be the voltage at this node? Like the maximum potential can be this V out maximum. V out maximum will be when this impedance is infinite, right? So maximum will be nothing but
Yes.
I into R. Okay, like the voltage drop across this resistance, right? So this will be nothing but 1 milliamps into R, right?
Yes. Yes.
So this voltage becomes 1 milliamps into R.
Yes.
Okay, and we are assuming, let's say, 1 milliamps into R is greater than 2 volt. Okay, assume, okay,
Okay.
assume
Okay.
R equals 10k. Yes, this is the case. Okay, so this will be 10 volt, right? Up to this, it is clear.
Yes.
Okay, so now it is charged to, let's say, 10
Yes.
volt.
Yes.
Okay, okay, 1 minute. So the charging is fast now, so it will be looking like this. Okay, this will hold, right? As the charging is very fast, it will charge to this. Okay, like this is exponential. Okay,
Yes.
now,
Yes.
okay, now again from
Got it.
t to 3t by 2. Okay, from t to 3t by 2, again the voltage, like the current source is open circuit because the zero current means open circuit, right? Same case will happening, so this capacitor will discharge through this capacitor, right?
Yes.
And again we are assuming that
Yes.
discharging is very fast.
Yes.
So this,
Again, exponential decay and very fast. Yes.
yes,
Yes. Very fast discharging.
okay, so this happens like in this, like every cycle it will be like this. So this will, so this is the transient and this is the steady state case. Okay, so the waveform will be looking like this every cycle. Okay, okay,
Yes.
because this portion comes only once.
Yes, yes.
Okay, so this is called transient, and this portion is repeated, like the cycle is repeating, so this we can call steady state. Okay, and you
Yes.
can find the average voltage of this steady state voltage, like V into T divided by T. Okay, area into time period. Okay, so that's all. So we can find the average voltage of this as well. Okay, okay, okay.
Yes.
Okay.
Now what is the
Understood.
time constant of the circuit? So for time constant, we have to remove the independent sources. So we have removed that. And what will the equivalent capacitance? So this will be nothing but,
C into R.
yes, C itself. And R means this R is like out of the picture, right? Because this is not making any
Yes, yes,
close path. Okay, across this
yes,
capacitor. Okay, so the effective impedance is this R only. Effective resistance. So this will be R. Okay, so this will be the time constant. Okay,
Yes.
okay.
yes,
So uh, can we make a circuit with inductor?
yes.
Okay, okay, let's do that.
Let's do it.
So for inductor, okay, let's have it. Okay, okay. Should I plot V out or IL, like I out? Okay, let's plot V out. Okay, so let's say this is a V of step 5 volt. Okay,
Yes.
so this is the V in. Now, how do you know that the at t equals 0 the frequency is
Infinite.
infinite? So the impedance are open circuited, right?
Yes.
So what will be the V out? So open circuit means the circuit will be looking like this.
Yes.
And the initial conditions of this inductor are zero, like, okay, the zero current.
Yes.
Now what will be the V out?
Then it will be 0.
It will be zero, right? Because there is
Yes.
only 1 volt, this is the ground, and this is 0 volt. So that t equals 0, the voltage is 0. Okay, no problem. Now what will be the, okay, so previously what we have all first order circuit, right? Because there was only one capacitor, right? Like in this case we
Yes.
can see there is only one capacitor. So this is called a first order circuit,
Yes. Yes.
first order system, or single pole system, or there are many names. Okay, so now okay, so now
Yes.
at t equals infinity, the frequency is 0, right? DC means the capacitor is short circuit, right?
Yes.
Like the, like, sorry, the inductor is short
Inductor is
circuit,
short circuited.
short circuited, right? So the picture will
Yes.
be
Yes.
looking like this, right? Right?
Yes. It is.
But like what now we have to comment what will be the V out. For this ground the V out is going to 0, and for this V in the V out is going to V in. But KVL is violated here, right? Because for a for a node they are all, like, there
Yes.
must be only one potential, right? There cannot be two potential. Here we can assuming, like, we can see that
Yes.
the node is short circuited to the V in, as well short circuited to the ground. So this is not possible, right?
Yes.
So now what will be the case? So the, like and we also know that the inductor can change the current through it when there is a infinite voltage through it. Okay, so exactly this case is happening here, right? Hello.
Yes.
Yes.
So okay, so let's, so this is not possible here, right? So basically this impedance is very low, right? Impedance is very low, and this impedance is very low. Basically we are assuming this is 0, but this is not exactly 0. This is like 0.000001, or this will be maybe 0.00001. Okay, like this. So we can make, and these two are in parallel, so effective impedance will be the lowest one, right? So the equivalent picture will be looking like this, right?
Yes.
And if we make L1 and this is L2, okay, now what will be the V out here? So this will be nothing but a inductive divider, like a resistive divider. So V out will be
Yes.
nothing
Yes.
but L2 divided by L1 plus L2 times V in,
L2 by L1 plus L2. Yes. Into B in.
right?
Yes.
Now the question is, will it be exponential, linear, or like what I can say, sudden, like sudden jump to the this voltage? This is the question.
If
Anyone?
there is infinite voltage change, then it will be sudden jump, I think.
Actually, what happening here is the current through the inductor becomes infinite in this case, right? Like there is no resist,
Okay.
right? Okay, try to analyze step by step. Okay,
Yes.
so now we can see that the current through this inductor becomes infinite. So when it is possible current through an inductor become infinite? When possible? When this VL is infinite, right? Hello.
Yes. Yes.
Actually, we will like go for step by step. Okay, so we can see that at t equals infinity, the like the impedance is very less for inductors, right? So we can see that there is a infinite current flowing through this both of these two inductor, right? Infinite
Yes.
current, and we know this expression for a the current through an inductor, and the infinite current possible when the VL becomes infinite, right? Right.
Yes.
Okay, now we are saying like the VL becomes infinite, right? Across these two, across these
Yes.
two inductor.
Inductor.
So there will be a, okay, let me do that. So I think there will be a sudden jump across this. Okay, voltage can go infinite like impulse, right? And then it will stay here. Is this possible, or this is the case, or this is the case? So there is three cases, right?
Yes.
Okay, let me do. Okay. Mm, so we are getting steady state voltage will be this. There is no confusion, right?
Yes. To get the exact expression, uh,
We can do the Laplace as well, but okay, let me draw the dual of this circuit, okay, with capacitor, okay. So the, okay, this equivalent will be nothing but this, right? And we are having V out here, and we have a capacitor here, and we have a voltage source. So there will be a current source like this, okay. Okay, forget it. Okay, so actually we are not going to write here, we will discuss in the next class, okay. So basically we have find the initial and final voltages like this, okay.
yes. Yes.
Actually
No
to
problem.
comment
Okay.
in hurry is not the way, okay. We will analyze it again, okay.
Yes.
Okay, so now basically we all know the property, but it will take time to solve it, okay. So we will do it
Yes.
in in our like coming classes. Okay. Okay. So
Yes,
now,
yes.
okay, so we stop here and we will discuss op amp. Okay, op amp as a block. Acha, how much time? Okay, we have time, right? So now we are going to introduce another very important circuit for us. This is called op amp. Okay, so we know op amp has a three terminal. Okay, positive, negative, and a output terminal. And there is, we can also make a supply rail for, let's say, plus VDD and minus VDD. So this is V plus and this is V minus. So we will try to model the op amp in this class and try to solve the circuit using op amp in next class. Okay, so we will try to uh, like write some
Okay.
properties of this block. Okay, so and op amp has a gain of A. Okay, so for op amp, what is the V out expression? So it takes the error voltage and it multiply with its gain to get to provide V out. Okay, so the V out expression is nothing but A times V plus minus V minus, and this is nothing but A times VD, right? So this is plus and this is minus VD. Okay, and we also know that the V out voltage cannot be more than VDD and cannot be lower than minus VDD. Okay, like if we plot the transfer characteristics V out by V in, so it will be looking like this, right?
Mm.
So this is
Yes.
plus VDD and this is minus VDD. We all know that, right?
Yes.
So the output voltage of the op amp cannot be more than the positive supply and the negative supply. Okay, like the V out will be like this if we make as a equation or expressions. Okay, now okay, so now what is the input impedance, output impedance, and equivalent model of a op amp? So op amp is a nothing but voltage control voltage source. Okay, right? So the
Yes.
voltage control voltage source is looking like this, and this is a dependent source. Okay, so this is the ideal model. So let's say this is VD and this is V plus, this is V minus terminal. Okay, so and this will be nothing but our V out, and this block is nothing but A times VD, right? And this will be also
Yes.
equal to this. So this is the ideal model. Okay, ideal model of a op amp. Now practically what we have, so for a voltage control voltage source means the input impedance must be infinite, right? And the output impedance must be zero for ideal case, right?
Yes. Yes.
But in practical case the model becomes this. So so this is the output impedance of this
Yes. Open.
op amp. Okay,
Draw a Rin across the VD.
okay, let make it. So RN is
Yes.
generally is very high. Okay,
Yes. Yes.
okay. Now the question comes, why a volt, like the voltage source having infinite input impedance and almost zero output impedance? There is like another topic, so we will discuss another video. Okay,
Yes.
so this is generally infinite and this is generally zero. Okay, and it takes the voltage difference and multiply with its gain and provide a output voltage. Okay,
Yes. Yes.
so this is the case and what I can, so and ideal op amp there is a offset there. Okay, offset means if we don't apply any input in these two terminals, by default there is a voltage source present there. Okay, inbuilt. Let's say this is V off. Okay, because this amplifier is made up of transistors and there are like threshold voltage mismatch, we all know, right? So there will be a like offset voltage across these two terminals. Okay, so actually when we haven't applied any input, it will V out get saturated. Okay, because the op amp gain is very high, so it will 8 times this V offset, right? So it will go to the VDD supply. Okay, or it can be minus, so it can go to the minus VDD as well if the V offset is minus. Okay, so this is the case. And generally, okay, one thing I forget, so A is generally infinite, right? The op amp gain, like the voltage gain, right? Voltage by
Yes, yes.
voltage gain is infinite. Now, okay, so this is the offset, and there is also bias current present here in practical life. So there is I bias there. Okay, so we will discuss it later. Okay, now, okay, so now this op amp as a transfer function of A of S, and basically in practical life this is a like frequency dependent, right? Because this is used like implemented using MOSFETs. So this will be nothing but V out by VD of S, and this is we are considering open loop, right? We are not going to do closed loop circuit yet. Okay, we will do that. So this will be nothing but, so they are having poles, zeros, and etc. And this can be first order first order like single stage op amp. Okay, single stage, maybe double stage, maybe triple state, like three state. Okay, three state cascaded. So for normally we can do the two stage. Okay, two stage Miller. Okay, right? Two stage Miller compensation op amp.
Yes.
So there is a DC gain. Let's say this A naught. So DC gain means the gain at DC frequency. So this will be looking like this at DC. Okay, this is the V out by VD transfer function in open loop. Okay, so DC gain times. So for two stage Miller compensation, there is a zero, and if we like there is a right up plane zero, right, for this Miller cap. So sy omega z, let's say, and there are two pole, one plus on okay, 1 plus 1 over omega p on 1 plus sy on plus omega p2. Okay, for a two stage practical Miller op amp, the op amp transfer function is looking like this. But in general case, we are neglect these poles and zero, and we are concentrate about this only DC open loop gain. Okay, okay.
Yes.
Hmm. So now let's make a circuit. So now we have a gain, DC gain of, let's say, 60 dB. 60 dB means 1000 in linear, right?
Yes.
Yes.
Actually in practical circuit we no need this like this type of like gain. Okay, and we are like we do feedback circuit, like mainly negative feedback circuit, to make the circuit more controlled. Okay, more controlled to us. Like we know that there is a process, voltage, temperature dependency in our electronic circuit, but we are we are trying to escape from this effect, right? So then what we do, we try to make like we try to use this op amp in negative feedback circuit. Okay, so what is negative feedback we will tell later. So let's have a negative feedback circuit first. Okay, let's say this is R1, R2, let's say this is V in here. So we can like make input here or make input here, that can be done. Okay, and the gain is A, and gain is almost, let's say, like very high, we have told that. Okay, now ideally what we do this terminal voltage is equivalent to this terminal voltage. So this is called virtual short concept, right? So
Yes.
I will be discussing in two way. Okay, actually this op amp is nothing but a integrator. Okay, this op amp is nothing but a integrator. Okay, an integrator having a unity gain frequency of omega u. Okay, so the model can be like this. So if I model this, this will be looking like this. Okay, so let me do that. So op amp is nothing but a integrator. Okay, so now the model will be looking like this. So let's say this is plus terminal and this is, let's say, minus terminal. Okay, so roughly this will be looking like this. Okay, Sijan. Okay,
Yes, yes. Okay.
so basically op amp is a integrator. Okay, so now, so why this
Yes.
virtual ground short concept has arrived? Because so we know that we need a finite output. We need a finite output, right? We don't need infinite output. Like infinite is not possible as well, right? So we need a controlled finite output, right?
Yes.
And we know that our signal, uh, like in electronic signal is in millivolt range or microvolt range, right. Now
Yes.
if we apply a small amplitude signal here, so it will need high gain so that it will get some volt range output. So now make this v out is finite. Let's say this v out is finite and we have a times v plus minus v minus. Now let's say we need a finite, so let's say this is 2 volt. Okay, and our a is very large, let's say this type of this. Now what do you think this voltage can be? So the vd is nothing but v plus minus.
Amit, I think
So this will be closer to zero, right?
yes. Amit, I
This,
think
yes.
the in this block there is a V in input,
Hmm,
right? And V out is output.
hmm.
So the unit of this block should be 1,
Yes,
as it is voltage by voltage.
yes.
So I think omega u into integration dt it is happening, na?
Oh yes. So you are saying this, right? Yes, so this will be the
Yes,
case.
yes,
Yes. This will be the case.
yes, yes.
Okay,
Okay, okay.
now this is okay. Now okay, so yes, so I was here, the gain is very large. Now to make this finite v out as 2 voltage, so this will be almost closer to zero, right? But not zero, it is closer to zero, let's say 0.000002 or something. Okay, so this is a like random value. Okay, for your example, so we have seen that
Yes, yes,
this difference voltage is very closer to zero. Okay, so that means
yes,
v minus is almost equal to v plus. So
yes,
there comes the virtual short concept. So we have seen that these two nodes is almost same, but there is no physical connection like a wire like this. Okay,
yes, yes,
so virtual terms arrives. There is no direct connection from these two nodes, but as the two voltage is almost same, so that we are considering there is shorted, like we know that if
yes,
there is va and there is also va, so we can directly sort this out, right? Short circuit it, we can do that. So basically virtual short concept comes from there. So they are not connected directly to the wire, but as their potential is almost same, so they are treated as same potential nodes, so they are called virtual short. Okay,
yes,
virtually
exactly,
shorted,
exactly.
they are
Yes,
virtually shorted. And another way, so this is the one way to think in virtual short concept. Another way is, what is the integration of zero?
Constant.
This is the constant, right? So that I have implemented this. So this block takes a almost zero input and give a finite output. So there is also meaningful the virtual short concept. Okay, like if this voltage is almost zero, na, so there is a finite output, right? We all know that.
yes,
Yes.
yes.
So if this is an integrator, then it is possible to make the input zero.
One can understood in this way also. Yes.
Okay, come again. I haven't listened carefully. Hello, Srijan. Hello.
Yes, yes.
Okay, okay.
Yes, one can think of this also.
Okay, yes. So this is the another way you can think of. Okay. So if this voltage becomes zero, so this voltage is finite. Not zero, okay, not zero. This is wrong. Not zero. This is a finite. So this is the another way you can think. So I wanted to tell this like in long time ago, but the time the time is now. Okay. So let's do now. Okay, let's make a
Okay.
circuit and try to
So
solve.
Amit, I think
Hmm.
yes, I think in the next class we will discuss about why this first stage and the single stage and the second stage is required, why there
Yes.
is Miller compensation,
Actually,
etc.
actually, Srijan, we will be going to do some non-inverting and inverting amplifier using op amp as a
Yes,
block.
yes,
Then we will try to do a
yes,
differentiator, adder, subtractor. Then we move to the like op amp design.
yes, yes.
It will
That
be
will be more exciting,
yes,
I
yes,
think. Yes,
yes, yes. Actually, we will be sharing some intuition behind this. Okay, in real life, like real life issues. Okay, why we cannot.
exactly.
Yes,
Then it will be very interesting for our viewers also. Yes,
yes, yes, yes. So okay, so can we stop here today?
yes,
So we will try to solve like inverting, non-inverting, and integrator, differentiator using op amp with adder, subtractor, and Smith trigger as well. Okay,
yes,
like
yes,
the most required components in practical life.
yes. And we can design with this op amp block and this much kind adder, integrator, differentiator.
Yes,
So that's why it is called the operational amplifier.
yes. Okay. Why operational? Why this is called operational amplifier?
Yes, yes.
Operational
We should
amplifier.
discuss this also.
Okay. Why operational? Why the term op amp? Because we can do many operation like many mathematical operations
Yes,
like
yes,
integration,
exactly.
like differentiator, okay, like adding, like subtracting, like we can use the exponential types of behavior and so on. Okay,
Yes, yes,
okay.
exactly.
So yes, so this is why the this amplifier is called operational amplifier. Okay,
Okay, okay.
okay, let's stop here. Okay.
Yes.